In this video, we describe a method of heading determination for a lunar microrover using solar light as an absolute reference. Planetary rovers estimate their map position by integrating incremental pose using wheel encoding, inertial measurements, and perception of terrain. However, these dead reckoning methods are prone to drift over time. Imperfect sensing, calibration, and imprecision of navigation calculations accumulate, creating inaccuracies in pose estimation that increase with distance traveled. One way to minimize this drift is by including observation data to some absolute reference. On the Moon, the Sun can provide this absolute reference. This research develops an absolute solar navigation system for MoonRanger, a small, fast, autonomous rover designed to search for ice in the lunar South Pole. Its small scale exacerbates slippage and limits the precision of its sensors compared to traditional, larger rovers. This makes its autonomous operations beyond the range of a ground station incur far more risk and creates a greater burden on the rover's autonomous navigation system. Maintaining an accurate awareness of its position and orientation is vital for MoonRanger's mission success. First, we will describe the heading determination algorithm. An ephemeris is a geometric time history for calculating relative position of celestial bodies at any time. We use this ephemeris to determine the vector describing the sunlight striking the Moon in moon map coordinates. We rotate this sun position vector into the coordinate frame centered on the rover's mission area. This vector describes the light as experienced by the rover. The rover's flight sensors measure two angles, the angular distances from the z-axis of the sensor frame. The field of view for both of these angles is 120 degrees, plus or minus 60 degrees, with error increasing near the limits. These sensors are located at the top of the solar panel, each pointing 30 degrees from the center line of the solar panel. We can convert their measurements into a unit vector pointing at the sun. These vectors are transformed into the rover body coordinate frame. Using inclinometer measurements that distinguish the robot's pitch and roll relative to the gravity vector, the observed sun vector is rotated into a frame that is flat, that is, centered on the rover, but whose xy plane is parallel to the lunar surface. This means that the frame of our measured sun vector shares its z-axis with that of our calculated sun vector. Finally, by computing the difference in azimuth between the measured and calculated sun vectors, we can estimate the rover's heading. Next, we will discuss the testing conducted to validate the algorithm. The sun sensors incorporated into the flight rover will be high in cost, precision, and lead time. Their utilization was not warranted for the purposes of this research. Our simulated sun sensor uses the sun vector from the ephemeris node along with the known orientation of the simulated rover to reverse the heading determination process, generating the nominal measurement angles. To these idealized measurements, we add Gaussian white noise consistent with the precision of the flight sensors. For our simulated experiment, we considered a case where the sun pointed directly west, a vector of 1, 0, 0. Heading varied from -90 to 90 degrees, thus keeping the sun within the range of the sensors. We varied roll from -20 to 20 degrees. The heading of the rover relative to the sun clearly affected the error. We see that the error is consistently low within the region where the two sun sensors' fields of view overlap and remains limited even until heading reaches plus or minus 60 degrees. However, past this point, the error quickly increases to more than 1 degree, a clearly unacceptable level. This indicates that the overlapping view of the sensors in the middle region helped to tame the uncertainty which was manifest at the edge. Knowledge of this increased error at the edges can inform the way this method interfaces with the overall position estimation algorithm. Giving less weight to these edge cases, we can benefit from the method when it performs well and avoid projecting its limitations on the overall pose estimation method. This research shows that the solar heading determination method for MoonRanger is a viable absolute reference method. In the future, the absolute heading algorithm must be integrated with MoonRanger's current dead reckoning pose estimation algorithm. Thank you so much for watching.